In this video, we're going to solve one practice question on simple regression. We're going to solve question 2 from chapter 7, and we're going to use data file LineSpeed. So here I have the question. In this question, we have, for an assembly line, we have the line speed, and we have the number of defective parts that are found for each line speed, for each observation, right? So we have the data set, and then we want to answer these questions. So we want to understand the relationship between the line speed and the number of defective parts that are found probably per minute. So we want to develop a scatter chart just to visualize the relationship. We want to, and then we want to comment on the relationship. Second, we want to develop a regression equation, estimated regression equation that can be used to predict the dependent variable based on the independent variable line speed. So line speed is going to be our predictor, and then the number of defective parts is going to be our dependent variable. All right, so we want to find the regression equation, and we want to then, in part C, we want to test the significance of the regression parameters, beta 0 and beta 1, the intercept and the coefficient for the line speed at 1% level of significance. So we just need to check the p-values, corresponding p-values for beta 0 and beta 1. If they're below 1%, then they're significant. If not, they're not significant, all right? And then make some comments regarding the interpretation of the estimated regression parameters. And basically comment on the coefficients. And then at the last part, how much of the variation in the number of defective parts, the dependent variable, found for the sample does this model explain. So that's just the definition of R squared. R squared is the percentage of variation, total variation in Y that the regression model explains. So we just need to read the R squared from the table, right? So I'm going to go to the, we're going to do them one by one. So I'm going to start with a scatter chart. So for the scatter chart, I just need to make sure that the independent variable, the predictor, is at the first column, which is the case here. So the line speed, so this is going to be X, Y. So that's by default how Excel is going to create the scatter chart. It's going to put the first column on the horizontal axis. So scatter, all right. And then getting rid of the grid lines, adding the axis titles. So the vertical is going to be number of defectives or defective parts, and then line speed. The number of defective parts also should be, this should be also rate, just to make sense. Like this should be per hour or per minute, or like there should be a unit of time, which the question did not mention. Anyway, so I have this scatter chart. In terms of the relationship that I observe, if I add a trend line here, if I right click on one of these data points and add a trend line, add a trend line. And add a trend line, add equation, and add R square. So for part A, draw the scatter chart and make a comment about the relationship. So from the trend line, we see that the overall relationship is a decreasing or negative relationship. As the line speed increases, the number of defective parts found decreases. All right, so there is a negative. So part A, there is a negative relationship between line speed and number of defectives. How do we know if this is negative, the relationship is negative? I mean, we can just observe that. And also from the slope. If you have just the equation, you can just look at the slope. Slope is negative, therefore the relationship is negative, right? So that's how we can make sure that we are getting it right. So part A, develop a relationship and make basically develop a scatter chart and make the comment about the relationship. Part B, use the data to develop an estimated regression equation that could be used to predict the number of defective parts found. What is the estimated regression model? We already have the regression model, but since in the next parts, part C, we need the p-values, the corresponding p-values for each coefficient. This is not going to give us that. So I'm just going to have to run the regression tool. So I'm just going to call it part B. And then I'm going to go ahead and use the regression tool. So I'm going to go to Data tab, Data Analysis, and Regression. So if I call the regression tool, Y range is going to be the number of defective parts found, and X range is going to be the line speed. And I do have labels. I included the first cells, B1 and A1, so I check for labels. And I'm just going to put it right after part B, D16. I'm going to also add the residual plots here because I'm going to make a statistical inference in part C of this question. So I'm going to check the residual plots. That way I can check the necessary condition for residual. All right, and then okay. So part B, we already had the equation, but I just want to make sure that we have everything that we need, which would be the p-values. All right, so the equation, if I want to write down the equation again, using this table, that would be number of parts or defective parts found. That would be intercept 22.17 plus or minus 0.14, actually 15, just round it up. I mean, even if you want to round it up with 3 decimals, it's going to be, 0.150 line speed. So that's the equation that we have, and it should be exactly the same as what we had here. Let me actually go with 4 decimals. That way we get the same. Exactly the same equation. So that should be the same because they're both using least squares method. So this should be exactly the same equation. And this is y hat, by the way. Y hat, or estimated value for y, is slope times x, x being here the line speed, plus the y-intercept. All right, so that's the equation. And then in part C, test whether each of the regression parameters is equal to 0 at 1% level of significance. So for this one, you just need to take a look at the p-values. And if the p-values are less than 1%, then that factor is significant at 1% level of significance. So intercept is significant. Why? Because p-value is lower than p-value is less than alpha. And alpha is 1%. Then the slope for line speed at 1% level of significance, this is not significant. However, at 5% level of significance, this is significant. And as you can see here, the confidence interval for beta 1, the 95% confidence interval for beta 1 does not include 0. So it's always negative. So that's actually a strong sign saying that the line speed has truly a negative relationship. But however, since we are taking alpha equal to 1%, slope is not significant at 1% level of significance. Slope is not significant at 1% alpha, right? How do we interpret the estimated values, the estimated coefficient? So this says as the line speed increases by 1 unit, the coefficient, as the line speed increases by 1 unit, the number of defective parts found decrease by almost 15 unit. So 0.15 unit is going to be the decrease in the number of defective parts found if the line speed increases by 1 unit, right? So that's the interpretation of the coefficient. But in terms of the significance, when we're just dealing with the p-value, we are just making a comment on the true relationship. If we are dealing with alpha of 5%, then p-value is less than 5% and the coefficient is significant at 5% level of significance, right? But if you're gonna stick to 1%, then it's not significant. So how do we fix that? How do we make sure that this is pretty close to 1%? So how do we fix this test? By adding to our sample size, by making a larger sample. That way you can be sure it's gonna definitely affect your p-value, and hopefully you're gonna get a significant coefficient, right? In part maybe, so we already, I think we just checked part C as well. Part C. So part B was this was part B, and this is part C. The significance. And then part D of this question How much of the variation in the number of defective parts found for the sample data does the model you estimated in part B explain? And that's just the definition of the R squared. So almost 74%, almost 74% or 73.91% of the total variation in sample in number of defective parts is explained by this model. And this model only has the line speed as the predictor. So basically, line speed is explaining 74% of the total variation in the number of defective parts in this sample. So just given this sample, we are able to explain 74%. So if you change the sample size, this may go up or down. If you change again the sample size, p-value may go up or down, and that's going to give you a better understanding of the true relationship between the line speed and the number of defective parts found.